So thank you very much, Gabriel, for the introduction and the invitation. So to Suresh and Jan, and yeah. So let's start. So I guess I have 1 hour in total, including questions. So I would do a little bit less than 1 hour then. So this work is based mainly in the work with my PhD student, Jose Jesus Perez Lona. But there are also some ingredients of previous collaborations and ongoing collaborations on the study of Calabi-Yau manifolds and applications. So as the title indicates, what we are going to do is to study type 2B string theory in one parameter Calabi-Yau models and explore for the discussed Swampland or quantum gravity conjectures. See? Okay, I will start with the motivation. Then I will describe to you what is the swampland and the landscape. And I will go to our model. Then, so we will pass to the 3 different conjectures that we are exploring here: the refined excited conjecture, the Transplanckian censorship conjecture, and a bound on the displacements of scalar fields coming from the existence of the species scale. And then I will conclude. So maybe the slide is not very needed here because it's for a more general audience. But so with string theory, in principle, so we have a theory of quantum gravity where there is room for the other fundamental interactions. And so if we want to make a connection to 4-dimensional effective theories, then this candidate to quantum gravity, a strong candidate to quantum gravity, that is string theory. So we need to describe the extra dimensions in with some special geometries if we want to reduce supersymmetry. So then Calabi-Yau manifolds have been studied. So Calabi-Yau manifolds have been studied intensively in the last 40 years or more. And so they could give rise to the extra dimensions of string theory. And so they allow to find 4-dimensional theories that they have n equal 1 supersymmetry. In the case of type 2B, after we add the oriented fold projection. So there are parameters. So there are parameters of the geometry, and those are complex structure or Kähler structure. Said in simple terms, so those are related to the shapes or the angles of the internal geometry, or they are related to the sizes of the cycles of the geometry. And we have the complex structure moduli, so they can be many, but in general, there are usually 3 kinds of singularity that appear in this space of moduli. So the conifold, the orbifold, or the large complex structure points. There are more also, and recently there have been more of the singularity studied. So what we are going to do is to obtain effective theories from the 10D strings. And one way of doing this is considering a warping. Considering a warping factor between the internal and the external geometry. And this warping can be useful in generating a scale difference between the 4-dimensional and the internal space. In particular, if one goes to conifold points, close to conifold points, these hierarchies of scales can be very strong. Okay, so here we have like a representation of these singular points of a moduli space for the mirror quintic. So one has this conifold, the large complex structure, that would be this one that is in green, that is the MOM, maximum omnipotent monodromy, or the orbifold. And so one needs to take the 3,0 holomorphic form of the Calabi-Yau and integrate it on the 3 cycles. And so if one considers these quantities that they are denoted periods, so we can solve around these critical points with some radius of convergence. And in this way, we can study the modular space of Calabi-Yau. So well, the conifold, so singularity can be desingularized, redundancy apart, in two ways, so via deformation or a resolution. But so here in this work, we work mostly in the regions of moduli space around the conifold or around the large complex structure point. So mirror symmetry is an important ingredient in most of the things that we are doing. And mirror symmetry exchanges scalar deformations with complex structure deformations. It has been intensively studied. And so in particular, one of the simplest compact Calabi-Yau that we can have is the mirror of the quintic surface in P4. And this is one of the examples that we take. And this geometry is very simple. I mean, it has one parameter, one complex structure parameter, but it has many size. It has many Keller parameters, so it's 101. But more recently, so in the last, let's say, 2 decades, many Calabi-Yau have been found that they also have, so they have one parameter in the complex structure, but they also have few parameters of sizes. So they also have few Keller moduli. And we also explore the case of 1,4 and 1,1 found by Candelas, De La Osa, and Brown and collaborators. So many years ago already, we studied this simple geometry of the mirror quintic, and we were exploring therefore hierarchies between the internal scale and the 4-dimensional scale. This was way before the discussions of the Swammland conjectures, but looking at this work from the perspective of nowadays, I mean, so we see that there we had some observations that they really put these models in the landscape. And towards the end of the talk, we will come to that. So what we are doing here is to explore the Swammland or quantum gravity conjectures. I like more the last title, in the one-parameter Calabi-Yau, in the complex structure moduli space, and also in the moduli space of the axial dilaton. So these are the 3 ones. Okay, this is a summary still. The refined de Sitter conjecture, the Transplanckian censorship conjecture, and the species scale. So, okay, for numerical examples, I already mentioned that apart from the mirror quintic, we are also going to explore this 1,1 and 1,4. And our results seem to match good with these Swammland conjectures. In a way that the refined de Sitter conjecture is satisfied statistically in hundreds of models with a lot of accuracy. And for the Transplanckian censorship conjecture, we are able to find something analytical in some of the asymptotic regions of moduli space. And we also perform several numerical studies that they agree with that. And of course, so there is where in the future it will come maybe machine learning, because so we have made numerical explorations, but limited ones. But in order to scale them, so maybe we will need some artificial neural networks. Okay.
No. May I ask a question? Why did you pick
Gabriel,
these?
thank you.
Why did you pick these 3 specific landscape conjectures and not some others?
Okay. Interesting question. I mean, let me think about the others. So, well, one of the first was the weak gravity conjecture, no? I mean, so here in these models, so what we have is a scalar potential, and we have a complex structure, axial dilaton. So I would say that, so as we have a scalar potential, these are the easiest to explore first, no? So you can see there are de Sitter, unstable de Sitter, what happens with the gradient of the potential. I mean, this, maybe I will go a little bit further here to some partial list of the Swammland conjectures I had. So these are related very much with the scalar potential, no? But in fact, this kind of setups is maybe also related with the distance conjecture, but it goes a little bit out of the scope of the model what we have, no? But the distance conjecture, so we will have to make fields evolutions that they are long and then see if there is a tower of states that become lighter. In principle, one could go and explore this in this setup, no? Okay. So maybe also this emergence conjecture.
Thanks.
So I would say it's simplicity because it's the first things that you can really test with the scale-up potential. So I mean, there is one very interesting thing that also in these Calabi-Yau compactifications, we have, so apart from this flux vacua, so we also have like the attraction mechanism and black hole solutions. So I mean, you have all solutions of the theories that they are these black holes. Maybe there one can also explore. So with the same techniques of Calabi-Yau, maybe one can explore there as well the species scale or order of the conjectures. But okay, so people have done statistics of these geometries. And as you probably all know, there is a statistics, so there is an estimation of how many flux vacua you can have, no? And roughly, so you can count the number of fluxes, L, and the number of cycles on a Calabi-Yau. And if you particularize for type 2, and you include the bounds coming from the tadpole cancellation and the constraints. So there is this 20 years old estimate that is 2024 now of how many vacua in principle you can have, no? So this really opens the possibility to statistics, or let's say numerical model studies. And of course, there are more recent, it's now 9 years, studies of what you can have in terms of vacua if you have a strongly coupled type 2B F theory, and this is like much higher. And then there are also discussions that started maybe 20 years ago, but then stopped. They have been more intensively pursued in the last years. And this is the discussion of the swampland and the landscape. And the swampland would be the set of all theories that they are apparently consistent semi-classically, but they are not really compatible with the quantum gravity theory. And so this would be this brown part there. And the landscape is the smaller set of theories where you can have a compatibility of with quantum gravity. And this thing has been discussed actively in the last 5 to less than 10 years, no? But yeah, so it has been discussed actively. So then, of course, so I don't think this is still settled, like how big is this landscape in the bigger space of semi-classical descriptions that then they don't have a completion at the ultraviolet regime. So then this is a way of measuring the landscape in the swampland. And this is one of the oldest conjectures. I think, okay, so this is the weak gravity conjecture. And so what we are doing here is exploring in this particular setup, that is the setup of flux type 2B compactifications. So where are these possible islands? So then there are many discussions, and I will cite like a partial list. So this slide that I was showing before to Gabriel, so I will show a partial list of these conjectures. And so they are called the swampland conjectures. So the weak gravity conjecture states that if you have a gravity with a gauge theory, so gravity is always the weakest force. And there are many examples. Of course, it's true in nature. It's true for our gravity in our universe. But in other theories that one can create of gravity together with gauge interactions, this is true. So there is the distance conjecture, and more recently linked to that one, the emergence conjecture, that states that if you have a potential and you have a field evolution, and this field evolution goes like a long distance in field space, then your effective theory will stop being valid, and you will have like a tower of states that they were previously in the regime of validity, they were very massive, but that they will become light. And so these three that we have in magenta here, the non-stable, de Sitter conjecture, or now called refined de Sitter conjecture because it was discussed and upgraded and so on. So states that you cannot have an effective theory that is compatible with quantum gravity or string theory, where you will have a stable de Sitter vacua. The Transplanckian censorship conjecture is more recent, and well, we will go to it, but basically states that if you had perturbations in the cosmological evolution, that they were very small, I mean, that they were of the order of the Planck lengths, so they cannot have an impact in the large scale structure. I mean, so they cannot have sizes that they are of the order of the Hubble distance. And well, this has motivations and from cosmology, and also it's also pretty discussed. And this bound on the species scale, this is due to duality, and this is also relatively old. I think it's more than 15 years old. I think so. And then the thing is that if you have a quantum gravity theory and you have species, so many species that they can be scalar fields, you will have like an effective scale below the Planck scale, at which, so if you start increasing energies, then your description stops to be valid, and you need the quantum gravity effects. So this one is the one that it has been discussed relatively recently, more, even so, so it was discussed a long time ago. And okay, the first one. So this non-stable de Sitter conjecture. So basically we have our scalar potential, and so we have a low energy theory of that is consistent with quantum gravity. Then we will need these two conditions to be fulfilled. Okay, the gradient, the absolute value of the gradient of the potential has to be greater, equal than a constant multiplied by the potential, or the minimum eigenvalue of the mass matrix, so has to be smaller, equal than minus C prime over B. I mean, basically this C and C prime, they are supposed to be order 1 constants. And so one simple example here, I mean, so scalar field, we have this gradient of B, absolute value divided by B, this, and yeah, okay. In Planck scale, it can be trusted in the regions where the field is bounded. The anti-de Sitter vacua, of course, they fulfill these two conditions. And this was made by these authors here, and later corrected by these authors. And there have been also, yeah, there was this also follow-up work where the refined de Sitter conjecture is coined. And of course, so people will say this is coined because so far it's complicated to find the de Sitter vacua. So in many of the construction, even so, there is the very nice setup of KKLT, but you can argue that things are not totally controlled, because so it is not that you are really finding like a whole, let's say, super precise vacua of the theory, but you have this step separation where first you take care of the axiodilaton and the complex structure, then you put these non-perturbative terms, and you stabilize the Keller, but it's a procedure that is like step by step. But of course, this is an ongoing discussion. And what we are going to do here is to explore, first to explore this one. So this drawing I have is an illustration of what this refined de Sitter conjecture says. So we have extrema of a scalar potential, and the extrema of the scalar potential, they are computed by having the gradient of B equals 0, okay? And then, so everything that I draw here colored in green, so this is supposed to be the landscape, and what is colored in brown is supposed to be the swampland, okay? So I have in the y-axis a cosmological constant, lambda, or let's say the value of the potential at the vacuum, and I have in the x-axis the minimum of the eigenvalues of the mass matrix also at the vacuum, okay? So basically, so going up here, so this is the Sitter, and under this horizontal line, this is anti-de Sitter, okay? And on the same, so if we go to the right of the vertical line, we have, so the minimum of the eigenvalues of the mass matrix is positive. This means, stable backward, and to the left, unstable. So, okay, so there are the regions. So stable anti-de Sitter, unstable anti-de Sitter, and this is the landscape. Okay, so this we did in a work now more than 3 years ago. We explored some compactification, some toroidal compactification with geometric and non-geometric fluxes. And using machine learning, we found a distribution of extrema. And if you see, the dots are very small. I'm sorry. So, but if you see, there is this line. So that I somehow mimicked there. So for this region of the landscape with a positive cosmological constant. And in this case, okay, so first we are going to do a similar exploration. So we have type 2b, a flux compactification, and this is an n equal 1 4-dimensional supergravity. So if we consider the internal space Calabi-Yau and we add the orientifold projection, and we will have a superpotential and a Kähler potential, okay? So this is the metric in field space. And basically, this is the potential that we are going to study. The KAB bar, this is the inverse metric. So we can compute the covariant derivatives of the superpotential. And the superpotential is given by the one of Gukov, Baffa, and Witten. And if we have some Calabi-Yau geometry, so this can be expressed in terms of the periods, okay? So we are integrating G3 form flux, a wedge, the 3,0 holomorphic form, and there, so we have this expressed in matrix forms where F and H are the fluxes, Ramon Schwartz, and pi are the periods, okay? And sigma is the symplectic matrix. So the Kähler potential can be expressed in terms of the axiodilaton. Okay, sorry, I didn't mention here. So in general, we have the axiodilaton, we have the complex structures, and we have the Kähler, okay? But we are focusing in the axiodilaton and the complex structure. So here we also have this term on the volume. And as I mentioned, the periods, they are the integrals of the 3,0 holomorphic form on the 3 cycles, okay? And these periods, they satisfy differential equations. And these differential equations are the so-called Picard-Fox equations. So we need the solutions of the Picard-Fox equations in order to describe the periods and compute this scalar potential. Okay, so, well, in these theories, we have, we can have Minkowski-Bakwa, and this has been explored by many people, but okay, so we did one exploration where, as I mentioned before, we were testing the hierarchies between the 4-dimensional and the 6-dimensional scale. And so one thing here is that so a mechanism similar to KKT is in a way invoked because, okay, so even so we may have more Keller moduli. So we are taking care first of the axiodilaton and the complex structure. And if you search for Minkowski-Vacua, well, so you can find many of them, and so they have very interesting properties. One of them is that near the conical, you may have hierarchies. So near the conical, in fact, so this is the solution for the complex structure in terms of the fluxes. And so if you adjust the fluxes, of course, you can go to some particular points, no? So you can get closer to the conical or closer to other points. Okay, so this is the story about Minkowski-Vacua that we are not dealing much, too much here. So what we started doing with the master project of Jose that now is doing the PhD, so is to explore the seated vacua of this kind of models, okay? And then, so Jose Perez Lona, that is doing the PhD here now in the University of Guanajuato. So he took the potential and just explored for extrema. And in hundreds of models, so what he found is that the refined de-Sitter conjecture was statistically satisfied, okay? Statistically means that there were maybe 4, I don't remember the exact number, cases where you do have a stable de-Sitter. But of course, so this is under discussion because you still have to take care of the Keller. And this is the first part of this project that now became a part of his PhD project. But if you see, I mean, this is a sector of this plot that we had here in this previous work. And okay, so this is about refine the seated conjecture. I will mention later strategies of how to improve this search and really see if we can place these models in the landscape or the sunlight. Okay, well, so now the second conjecture we are exploring, I'm looking at the time. Okay, I'm okay. So is the, okay, so I had all these slides were called cosmological field evolutions before, but this morning, it's my morning, you know. So I look at the talk and I remove the cosmological word from all the slides because we don't know if this is a really cosmological field evolution. But of course, the Transplanckian censorship conjecture is inspired in cosmology. So it's inspired in cosmological applications. But this I tell you, I will tell you later why we don't know if this is appropriate for cosmology. And okay, so we have now 4 scalar fields, R, theta, tau, T1, T2, and we have to look at the kinetic term of the Lagrangian, we need to canonically normalize it. I mean, this is just for physical applications, okay? Well, so this can be done, of course, because this is an n=1 4-dimensional supergravity, so you have this metric in field space, but you can diagonalize it, or let's say make it canonical. And yeah, once you have this, you can also talk about what happens. Okay, so how much the canonical fields will displace in this multi-field cosmological evolution. And let me go to the Transplanckian censorship conjecture, okay? I will briefly explain it. So if we have a field theory that is consistent with quantum gravity, this is, I'm stating it, okay? Does not lead to a cosmological expansion where any perturbation that has length scale greater than the Hubble radius, you can trace it back to Transplanckian scales in an earlier time. Okay, time goes flying, and I saw this is newer, but okay, this is already 6 years And, and basically, you can write this in equation 10 in terms of the scale factor, the Planck scale. I is initial and F is final, okay? And basically, you have AF over AI, okay? So it's the scale factor at the final stage and the scale factor at initial stage. And you can relate this with the current whole scale, okay? If you impose this, and I think this is desirable for cosmology, or at least it's something that it has been under discussion, Bedroya and Baffa showed that then the scalar potential, even if it's a multi-field scalar potential, okay, needs to fulfill 11. I mean, first they did for one field, and then they did for multiple fields, and this S, yeah, so it's the affine parameter of the evolution. I mean, basically, you have, you need that the derivative with respect to the parameter of the potential over the potential is greater equal than square root of 2 over 3, okay? Of course, it depends on the dimension. And yeah, so this is the Transplanckian censorship conjecture that we explore here next. Interesting, in an interesting way, we started doing numerical studies because our final goal was to do so also like a machine learning exploration of that. I mean, now this is postponed for the following project, but there are also analytical results. I mean, there are generic results in the one parameter family. Okay, well, these plots maybe don't say so much to you. This is just for you to see that we did computed numerically evolutions, and this is a particular flux configuration. But you see, okay, maybe it says this. So if we are looking here, I think I didn't wrote it there, but I think, oh no, it's written there. So we are looking there at the conifold region of the complex structure model space. And yeah, we would say this is violated. Okay, but then there is something I didn't say precisely. So this conjecture of Pedroia and Baffa states that you have this relation, but if you move in the asymptotic regions of model space, okay? And so these first cases that we studied, this is not an asymptotic region. I mean, you would say, okay, a conifold singularity, I mean, so the singularity, so it's a critical point, no? So maybe this is like a boundary of model space, but not. So it's not an infinite distance. So if you can compute the distance on model space, it has a finite distance. But there is another point of these singularities that indeed it has a like infinite distance, and this is the large complex structure. So it's not strange that here, yeah. So it seems that you don't have in the numerical things we explored that you don't have this bound fulfilled. But for example, okay, these were again numerical explorations. So if we look now at the large complex structure region, so there is infinite distance if we go from some point in model space in the direction of the large complex structure. And then, yeah, okay, this is the same numerical example, but now in this region, okay? And the conjecture is fulfilled. What it comes, they are just plots of the same thing. I mean, these are different evolutions that Jose computed. Okay, some of them look more obvious than the others, but basically these are all numerical exploration in the large complex structure region. So this is the potential evolution, but okay, now this is the derivative of the potential with respect to the parameter over the potential. Okay, this can also be translated in the gradient of the potential, and numerically for the tens of cases studied is fulfilled. Okay, but in this case, we can do a little bit nicer. If we have, Damian has a question. Let me, okay.
Right. Hi, Nana. I have a question regarding the, can you hear me?
Yes, yes, yes.
I had a question regarding the initial conditions for the field evolution.
Yes.
So you just determined the field value, the initial field value is being close to the large complex structure, or?
Yeah, it's a little bit tricky. I mean, yeah, so we determined them like that because otherwise it was hard like to identify many trajectories that go to their, yeah. So we basically took regions relatively close to the large complex structure.
Okay, but basically depending on the initial conditions, you might, I mean, so how do they how do the evolutions differ for each of these, depending on the conditions that you pick?
Okay, so Jose has studied many conditions, but it's not exhaustive. I mean, it's basically just of the orders of tens. I don't know, 40. It's not like an exhaustive numerical exploration. But basically, what it appears is that it is always fulfilled. That if you are close enough to the large complex structure, I mean, how close you have to see, this gradient of B over B goes over the yellow line. So it seems to be generic, but it's not like, yeah, a very wide numerical exploration. But there is something nice coming here analytically in the limit of the large complex structure, apart from the numerics. So this, in fact, yeah. So in fact, in this asymptotic region, there is something nicer than just the numerical exploration. But you are right. So I mean, we use the trick of starting close. Damian?
Yeah, okay, thank you. Yeah.
Okay. Thank you. Yeah, I mean, yeah, you can tell me more later. But so now I was coming to this a little bit generic part. So if we look at the periods in the large complex structure region, so one can use the Frobenius basis and solve these Picard-Fox equations. And you have like a list of one parameter Calabi-Yau that they have hypergeometric Picard-Fox equations. So these hypergeometric Picard-Fox equations, they have, yeah, a particular way of the solutions in this Frobenius basis. And for this family, you can write, I mean, you can find the symplectic basis by multiplying this shape of the solutions for this matrix where you have topological data of the given Calabi-Yau, okay? So this was done years ago, and more recently, it has been discussed. So this hypergeometric one-parameter family have been discussed. And if we do that, okay, we will see now what happens if we look near the large complex structure. So, okay, so this is a more, I'm sorry, okay, let me see. So this is a, okay, it's a particular shape of the periods that we wrote very near to a large complex structure. I mean, basically, these are the leading terms. So if we compute, if we go in this asymptotic region, and we find that the leading term to gradient of B over B, absolute value, is this term here, depending on the coefficients, okay? And then we did many numerical studies for the mirror quintic, and yeah, so it seems that always this was the result. But then if we look at this hypergeometric family, these coefficients, of course, depend on the topological data of the Calabi-Yau, and the condition is fulfilled, I mean, analytically. So just the way of having the large complex structure periods in the symplectic basis in this form, you can find that this Transplanckian censorship conjecture is satisfied precisely in this asymptotic in this asymptotics of moduli space, basically in the large complex structure limit. This is quite nice. So, but I mean, I don't know if it's generic. I have to think, but I don't know if it's generic for all, one parameter, or if it can be more generic. Maybe it can. but so far for this hypergeometric family, in all of this Calabi-Yau, this asymptotic direction, we find agreement with this Transplanckian censorship conjecture, okay? And, okay, in the other, let me now a little bit accelerate. I saw that there is a lot of time, but the time is flying. And now there are other asymptotic regions. The asymptotic regions of the axion or the asymptotic region of the dilaton. Of course, here, where we want perturbative string theory, G string smaller than 1, but okay, this is G string 0 limit, but this is also an infinite distance limit. And here we can compute this recently Jose computed, and we are discussing it now. So you can compute also what happens to the bound of this Transplanckian censorship conjecture in these two limits. And this seems to be more model dependent because these Pascal A, B, C, E, F coefficients, they depend on the periods and then depend on the fluxes. But yeah, maybe it can be simplified. The funny thing is that all numerical evaluations so far that this have been for the mirror quintic, they fulfill the Transplanckian censorship conjecture also in these regions. And okay, here I have two plots that Jose recently did. And these are, for example, different fluxes, and this is gradient of B over B, no? And this is, yeah, so this is for tau 1 large, for the axion large, and for the dilaton, for tau 2 large, we also find this. Okay, this is, sorry, I mean, you don't see much changes in many of these things because these are run for smaller times, I mean, for smaller times. But basically, what we are finding in the numerical explorations is that also the Transplanckian censorship conjecture is fulfilled. Universality, we don't know yet, but numerical explorations go in that direction. Okay, and the last conjecture I wanted to talk to you about is what happens with the bounds coming from the species scale. Okay, so I'm missing a slide explaining what the species scale is, although I mentioned it before. So Duali found it by saying, okay, so I have a theory of quantum gravity and I can form black holes, yeah, in this theory, and there are n scalar fields with some symmetries, species, that they have a mass scale, okay? And then, yeah, so there is an effective quantum gravity scale in the way that the sizes of the smaller semi-classically good behaved black holes, they have this species scale. But okay, so here in this slide, we are talking about recent discussions and applications to this swampland thing coming from that. Okay, last year, there were already papers. I mean, there were papers. I think this paper already has like 35 citations. I mean, people are discussing that. Basically, where you can bound also the scalar field by this species scale. It's related to the emergent string conjecture. And this last tells you that these light modes are arising at infinite distance. If you take this bound coming from the existence of this species scale, you find that there is a maximum diameter of evolutions of the fields. And this is 15, okay? So this is where you have these coefficients A and B. And basically, this is in agreement with what you find in these models, okay? So what you find in these models is that for all numerical explorations that you do, you have that the displacements of the fields, potential cosmological evolutions, they are pretty much bounded by the Planck scale, or I mean, they are smaller, in general, much smaller than the Planck scale. So this is what I said before, that I would finish with an old work where we observed this here with Oscar Loaiza and Yvonne Zavala, that if we were exploring for potential inflationary regions. if you explore for these potential inflationary regions in the complex structure axiodilaton model space, what you find always is that the displacement of the canonical fields is pretty much bounded by a scale smaller than the Planck scale. And this occurs here too in these evolutions, in this multi-field evolution. I will conclude to saying that we started these explorations first to try to see if the machine learning technology that in the work with Cesar, Damian, Oscar Loaiza, Damian Mayorga, that is in the audience, and Alejandro Montañez, we were constructing neural networks in order to classify thousands of flux configurations. And I think that this can be easily applied here, the same method, okay, to distinguish between, Bagua. Okay, sorry, here I have, this statement is not very good because for that we will have to incorporate Keller moduli, okay? So here we either have DS or Minkowski, but so we can use this to distinguish in these more complete models between ADS or DS, or also I missed to write here between stable de Sitter, unstable de Sitter, and we can also use a classifier to distinguish between these models that have these constants of the refined de Sitter conjecture much smaller than 1 or of the order of 1. Okay, so basically it's a construct, a classifier on artificial neural network that assigns flux configurations with the landscape or the swampland, and it's pretty much similar. I mean, this is an extension of this work that we did now more than 3 years ago. Okay. Also, one could maybe apply this to study the other asymptotic regions, okay? So the regions of the axion, asymptotic regions of the axion or of the dilaton, and these neural networks serve as classifier, okay? So you can, basically what it would be efficient is that you can say if these bunches, thousands of fluxes configurations, they are satisfying the conjectures or not. About the geometry, I don't know, but maybe one could do this exploration. So I said this before the conclusions, but it's part of the conclusions. So what we have done is to explore these three conjectures for the scalar potentials of effective string theories, refine the Sitter conjecture, Transplanckian censorship conjecture, and the bound of the fields by the species scale, okay? And we did in the family of one parameter type 2B Calabi-Yau's. So refine the Sitter conjecture is explored numerically, and it seems to be fulfilled statistically in most of the models, but there are models in tension with it. So the Transplanckian censorship conjecture is fulfilled in one of the asymptotic directions of the one parameter models, but previously to that, we also did numerical studies. The displacement of the scalar fields in this model seems to be also compatible with the species scale. So we need really to make a further data scan, okay, to make like a more efficient data scan in a second stage, okay, for Jose second PhD project. And machine learning may be useful in that. Of course, one has to explore the KKLT. Okay, so here I didn't mention it, but okay, these are also some things we are discussing with Damian and Yvonne. Let's see. So also we need to study the discussions that have been active in the last 10 years of what happens of the compatibility of this solution with the equations of motions in 10D. I conclude with a Mid-Journey image of what would be a landscape of physical theories, or what would be a string theory landscape. This was what Midjourney did when I asked this some months ago. And I thank you for your attention.
Thanks very much, Nana, for this nice talk. Thank you.